welcome everybody. And I'd like to thank Dr. Chen here for coming and speaking with us today. Dr. Chen got his PhD at Michigan with Jesse Grizzle, is that right? And then a postdoc at Caltech with Aaron Ames during this period of work has worked in many different application domains, so ranging from ground and aerial robotics to power networks, but now has been snatched up by NVIDIA and is focusing on autonomous driving. And so Dr. Chen is now a research scientist with the Autonomous Vehicle Research Group at NVIDIA. And he has graciously agreed to talk to us today towards safe multi-agent autonomy. So with that, take it away. Thank you, Dr. Chen.
Thank you, Silva, for the invitation, and I'm very excited to talk to you guys. So before I start my talk, I would like to say two things. First, I'm still like some of you already heard that I'm still coughing, so I'll try to make myself muted when I have to cough. The second thing is the goal of this presentation. You'll soon see that the presentation consists of two parts. The first part is more on the control side, and that's more like the work I did during my PhD and postdoc. And that part, I do hope you guys can take away something and then maybe just even apply it, because I feel it's if you understand the detail, it's not very difficult to apply that to some of your problems. And the second part is more on the autonomous vehicle, forward-looking. It's work that I have been doing since I joined NVIDIA. So yeah, it's more on the. I won't go into that much detail. It's more like just gloss through what I've been doing, and then it's all obviously related to the safety side of the things. And yeah, so let's get started. And please ask questions if you have any. Don't worry about interrupting me. I hope I can clear up your confusion right away. Okay. So yeah, today's topic is on multi-agent safety. And why do we worry about that? Why is this a thing that's worth discussing? Well, first of all, multi-agent systems are naturally difficult, more challenging than single-agent systems. And one of the difficulty comes from just the sheer size of these systems. Like dimensionality becomes super high when you have a lot of agents. And the second thing is non-cooperative agents, which is something we have to deal with all the time during when we're, for example, in a system like autonomous driving. So somebody even asked, like, is guaranteed safety even possible? And I believe for many of you, the gut feeling is that, well, for autonomous driving, it's probably not even possible, right? So let's talk about the two parts. So the first part will be about systems where you have control over the whole system, and it's more about tackling dimensionality. And the second part is more about tackling non-cooperative agents. So I'm not sure which part of the what background is this crowd? Has Silvia covered control barrier function or not? If not, let me just briefly review the concept, because that's what I did, what I've been doing for, I don't know, 8 years, counting PhD and postdoc. And that's the tool I'll be using for the first part. So control barrier function, sometimes referred to as a CBF, is a concept that hopefully we can guarantee safety with CBF, and it deals with dynamic system, a generic dynamic system. It can be nonlinear, written in the following form: x dot equals to f of x and u, where x is the state, u is the input. This is a classic setting, and the goal is to always keep the system within a safe set C. And to do so, we basically write down a scalar function h, and that's the control barrier function, the CBF, which is a function of the state only. And we can define a zero-level set of this CBF h, and that will be our safe set S, which should be a subset of our constraint C. So in other words, if you can keep the CBF always positive, then the state is within this S set, and then subsequently it's within the safety boundary of C. So this is the rough idea of CBF. And to maintain this, basically we have to enforce a condition called the CBF condition, and it's in the following form: H dot plus alpha of H is larger than 0, or sorry, non-negative. This alpha is called a class K function. You can think of it as a function that's monotonically increasing and pass through the origin. In other words, when H is positive, alpha is positive, alpha H is positive, and when H is negative, alpha of H is negative. So, the typical function is just a linear function, right? So if this is true, then what will happen is that when H is negative, in other words, X is outside the set S, the CBF condition will enforce H dot to be positive, which basically pushes all the state back into S. And when H is positive, in other words, you're already inside the set S, then you are allowed to have negative H dot. But basically, when you're approaching the boundary, the CBF condition would keep you inside the set. So that's why we can guarantee safety. Of course, it's not that simple. You cannot just like write down the CBF QP and then solve it, and then everything will be good. Because you don't always guarantee that this CBF QP will have a solution, right? Oh, sorry. I probably should have talked about the CBF QP first. So CBF QP is usually how we enforce safety. And the setup is that you can have some legacy controller that generates a legacy control input U0, which can be, for example, your MPC, your LQR, whatever you want. Then you add on top of it the CBF QP, which is minimizing the difference between the actual input U that you send to your system versus the legacy controller input U0, such that the CBF condition is satisfied. So if U0 naturally satisfies the CBF condition, then you don't change anything. If it doesn't satisfy, then you do the minimum, you add some minimum change so that it satisfies the CBF condition. So like I said, this is not always guaranteed to be feasible. And to make sure that it's always feasible, so that we can actually guarantee safety, we have to make sure that for all the X inside our safe set C, there always exists a U in the feasible input domain, such that the CBF condition is satisfied. And that requires a controlling invariant set. And controlling invariant set definition is that if you have a set such that as long as you start inside the set, you can always find control that keeps the state inside the set, then this is called a controlling invariant set. So I'm sure you guys have heard of, you have studied Hammond-Jacobi. Hammond-Jacobi is a nice way to compute such a controlling invariant set. But as you might know, this is not easy, right? Like even Hammond-Jacobi, you have to solve this PDE, which is quite computational demanding. So to further kind of explain why controlling invariant set is so important, let's consider a very simple example of a double integrator, where you have two states. S is your kind of distance traveled. You can think of it that way. V is your velocity, and your control is basically the acceleration. So control is usually within some bound, because everything in the real world has a bound. You cannot have infinite acceleration. And let's say we have some constraints such that S has to be less than some constant C, right? Then can we directly use the constraint function as CBF? Let's say, let's just construct CBF simply as, oh, sorry, this should be capital C minus S, right? Then if H is positive, then constraint is satisfied. If it's negative, then it's not satisfied, right? Can we just directly use this as CBF? It turns out no. All right, why? Because we can draw this diagram where you can see that the x-axis is S, the y-axis is velocity. So that's the state space we're talking about. And we have this constraint S equals to C. So basically we want our state to always stay on the left side of this vertical line, right? Then basically if we take H0 to be our CBF, then everything on the left side of this line is our, let me go back, is our S, right? That's the zero level set. So zero level set is simply everything on the left side. But if you're inside this cyan region, you'll find out that your velocity is so high, and because of your acceleration is limited, so your velocity is too high, so that the inertia will push you to violate this safety constraint. So in other words, this is not a control invariant set. And the actual control invariant set is actually the purple part. So if you're inside this purple part, you do have enough time to stop the point before it breaches this safety constraint. And that's a well-known CBF, which is basically this guy, where the difference is that we add another term that is counting the minimum braking distance, right? So if you're driving, you know exactly what I mean, right? When you're at a certain velocity, it takes some distance to slow your vehicle down to a full stop, and basically we simply subtract that part from the original CBF, then we get an actual valid CBF. Yeah, so this is a simple system where you have monotonicity, you have a very simple linear dynamics. So all those special conditions make it simple to come up with a nice CBF. But what about a general system? This is where people have been struggling, right? There are a lot of methods that have been proposed to compute control invariant set, for example, Jacobi. That's something you definitely know about. There are polytopic methods that's doing like robust linear programming. You have sum of squares, many other computational methods, but they all suffer from the common issue, which is this is my personal view. I think the real difficulty of these methods is that it's just really hard to explicitly represent a set, right? If I ask you how can I represent a set which is of arbitrary shape in high dimensional space, right? You can do discretization, which is what Hammond-Jacobi does. Then you have the curse of dimensionality. When the dimension becomes high, computation becomes really difficult. You know, you run out of memory very quickly. You can use a level set of some smooth function, for example, polynomial, polytopes. Then you're limited by your representation power because these functions are still like simple functions. And you have like brittle numerics, especially in the case of sum of squares. You'll soon find out, if you have some experience with that, you know that when the polynomial degree goes to say 8 or 10, very easily you get like backscaling, and then your LMI becomes difficult to solve. And some people have been using neural networks. Obviously, it has very strong expressibility power, but because of the way we train neural networks, it never has this kind of like bulletproof 100% guarantee, because everything is just a loss. So, you know, you can only kind of like roughly ensure safety, which is less strong as these methods. So in general, I think there's no magic formula yet, at least for explicit method. But what about implicit method? So this is the method that I want to introduce. So let me give you some background. If we consider a general nonlinear dynamics, like before, x dot equals to f of x and u, then we can think about any time invariant feedback control policy pi. So this is just a mapping from your state to an input. Then we can write down this closed loop system under pi as f pi, right? That's just your standard like dynamic system course. And the next thing is we want to talk about is called a flow map. So what is a flow map? A flow map is basically a mapping from the current state to the future state, assuming the state follows your backup policy. Of course, this doesn't have to be a backup policy. It can be any policy, right? Any policy pi, we can basically just forward integrate the dynamic system, and then we reach and then given a certain horizon, we can reach at a future state. So we define this flow map that maps the current state to that future state. Okay, so then let me give you an example. So let's consider this f pi equals to just some stable dynamic linear dynamics. Okay, and you know that for stable linear dynamics, it basically converges exponentially towards the origin. Then here, what I'm animating is, let's consider this state. So let's say this is the current state, right? So the current state is actually moving in circle, so which is not following this policy. But we can forward integrate the system, and then we pick some horizon, let's say t equals to 4 seconds or 8 seconds. Then this is the actual trajectory. If the system follows the backup policy, then it will reach this point when it's 4 seconds, and it will reach this point when it's 8 seconds. So the flow map basically maps this point to this point if you take t equals to 4, or this point when t equals to 8, right? And so this is basically just animating how the current system, the current state got mapped to the future state if it follows the backup policy. Then we can talk about an implicit representation of control invariant set and subsequently CBF. So let's do this thought experiment. Let's consider, again, we have some safe set to begin with, and let's call it HC. Let's say we assume it can be represented as zero level set of some function, right? Then we want our state to always stay inside this yellow set. And let's assume that for some reason that you happen to have a control invariant set. I know I said that control invariant set is very difficult to obtain, but let's just assume right, you have a small control invariant set to begin with, and later you'll see that when you don't have much requirement for this control invariant set, for example, you can live with a very small one, they are actually easier to obtain, right? Just by some simple method, you can actually get some very small control invariant set. Then I want you to consider all the points such that if we just forward integrate from some of the points here, following a fixed policy, we call it backup policy f pi, like I introduced in the last slide, and eventually this state will be will converge into this S0, this small control invariant set, and in addition, the whole process, the whole trajectory stays inside the safe set C. So I want you to think about all these points that satisfy these two conditions. First, it can reach the final small control invariant set. Second, the whole trajectory in between satisfy the safety constraint. Then my argument is that all these points form a larger control invariant set, right? So, and the reason is that the definition of control invariant set means if you're inside the set, you can always stay inside the set. So let's see if this is true for this purple set. When you are inside this purple set, the reason why I can say that you can stay inside this purple set forever is because you can simply ask the point to follow the backup policy, and it will reach the small control invariant set. And once it's reached the small control invariant set, because this is a control invariant set, you can stay inside the small set forever, and subsequently you're inside the purple set forever, which satisfies the definition of control invariant set. Okay, so that's an implicit representation of a larger control invariant set that hopefully can be more useful than a small one. And you can notice that this point is not counted. It's not included in the purple set because it violates the safety constraint when it's reaching the control invariant set under the backup policy. So this is really the critical step for backup CBF. Any question here?
I have a quick question. Are you making some assumptions about the points you haven't sampled in this purple set of where you can draw the boundaries of this?
Yeah. So so this purple set, we don't do any sampling. We're not sampling points and kind of verify that it will satisfy the constraint. We're simply writing down this condition, and we'll use this implicit representation throughout the whole process, and no sampling is actually required. So you can actually see that the purple set is actually defined here. It's a rather complicated representation, but really the idea is that we're using this definition of flow map. So you can see that we're implicitly defining for all the points such that if the flow map acting on X at the end of the horizon T is inside the small control unit set S0, and for any small t that's between 0 and capital T, the flow map will not exit the safety constraint, then this is basically our definition of the purple set, right? It's really just the two conditions that I mentioned, and we write it down using this flow map. So flow map is really a convenient way to define such an implicit set. Okay, so then basically we have the theorem that I just mentioned. The purple set is indeed a control invariant set because of the proof sketch is just what I described, right? You just follow the backup policy, and you will reach the S0, and then you can stay inside the S0 indefinitely, which is feasible. So then, okay, the next step is, okay, now we have a control invariant set. The next step is just to write down a CBF, right? And then we take exactly this definition here, this set definition, and just turn that into a scalar function. So here you can see hx is defined as this function where it's the minimum over the two, where the second term here is basically ensuring that after the horizon capital T, you'll reach the small control invariant set, right? It's just the composition of two functions, the flow map and hs, which is defined as, so the zero level set of hs is our small control invariant set. And the first term is basically it's for the condition such that every point in between you don't exit the safe set. So we're taking the minimum over the horizon, and then composing the flow map with the larger safe set definition. Now, obviously, this function is still quite complicated. It's still an implicit function. We cannot directly put that into CBFQP, but later I'll show you how to actually compute the derivative of this H. So it's quite daunting here, but really we're just taking the derivative over the flow map. So even if flow map is defined sort of as a mapping from the current state to the future state, we can actually compute the derivative, and that's the interesting part of this approach. So H dot, actually, I won't go into detail here, but really you can think about like there are two parts. The first part is how we deal with the first condition, and then the second part is how we deal with the terminal condition. So I'll first argue that when we make when we differentiate the flow map, I don't know if you have taken a course in like fluid dynamics, you'll be very familiar with this kind of total differentiation, right? When we're differentiating over something that's like a time varying how do I say that? It's a time varying flow. Then you usually get like two terms. One term is the partial derivative with respect to time, and that's like your carrying speed, so to speak. Like the flow itself is moving forward, and that's why you have a derivative like that. And the second part is how you move with respect to the flow. So we have exactly like that. So we have the partial derivative with respect to time, and this is basically describing your future state. If you follow the backup policy, how does that point move with respect to time? And naturally, this is just equal to the backup policy acting on that point, because as time moves forward, that point is just going to follow the backup policy moving forward. So yeah, this is just f pi of that point. But the second part is the sort of how you move with respect to your backup policy. And requires us to compute something called sensitivity Jacobian. And this guy is really just, let me kind of visually describe what this point is. So you can see that this is the example that I just showed. This is the current point, and then after the backup policy, it got moved to this point. So the second term is really describing if I move the current point in an arbitrary direction, how will the endpoint, so how will the flow map, sort of the point that the flow map maps to move in response. So you can see that when the red point is like circling this red circle, this future point is also making a smaller circle. So really we can define a Jacobian such that describes if this red point moves around, how will the future point move around? So that's really the Jacobian we're talking about. And that Jacobian can be directly solved with something called an adjoint ODE. And actually, if you don't know, many of your ODE solver, for example, ODE 4.5, already calculate that for you. That's an important thing that they use to kind of determine the step size they take in the Runge-Kutta step. So really, for any dynamic system, you can simply use this. You can simply write down this adjoint ODE, which is another ODE to solve. So you can just get this sensitivity almost for free. So now with these terms computable, we can basically actually write down the CBF condition with these terms, right? And one thing that I want to emphasize here is that we have this proposition where if we simply take the control input to be the backup policy, then H dot will equal to 0. Okay, so this is again something that's I mean, kind of give you an intuitive explanation. So H basically describes the margin you have, the margin to satisfying these two conditions. The first condition is you reach the small set at the end. The second condition is that you don't breach the safe condition in the middle. So H is really just describing the margin. It's measuring the margin of the two conditions. So H dot is saying, if I move around the current point, how will my margin change in time? Okay. So naturally, if you just follow your backup policy, then you're simply moving along this line, then your margin will not change, right? So naturally, H dot equal to 0 when you just simply plug in the backup policy. And that is basically all we need, because that ensures that we will always have a feasible solution to our CBF QP, because we know that U equal to pi of x is a feasible solution. So now we have the CBF QP constructed, we can compute it, we have all the derivative we have, and then we know that it's always feasible. And that's why this is a very nice, almost free control invariance that you can use for CBF QP. Any questions? Okay. Let's look at an example. I know it's a bit I know it's a lot of information to process, but let's look at an example. This is the same double integrator example that I just showed. And I'm gonna reconstruct the nice CBF QP, sorry, the nice CBF that I mentioned before with this backup policy approach. So this is our well-known CBF, right? And let me just pick S0, our small control invariant set, to be this, where it's defined as velocity equals 0 and S is less than C. In other words, it's just this blue line, right? That's extending left to the left. Why is this a nice control invariant set? Because since V is 0, right? As long as U is 0, you can always stay on this line. and it satisfies the safety constraint. So this is a nice control invariant set that's within our safety constraint. And let's just pick pi of x to be this maximum, like always use the max braking to go to zero velocity, right? So when velocity is positive, you take a negative acceleration and then converge to the blue line, and when it's negative, you do the opposite. And you'll see that the state will basically move along these lines, right? If you just these are like parabolic curves that's under the maximum braking, and you can actually verify that if you write down the backup policy CBF like this, you get exactly the well-known CBF back. Okay, because this flow map now becomes this sort of parabolic curves, and you can verify for yourself, but really you just recover this nice well-known CBF. So in other words, this for this very simple problem, the best CBF we can find is actually a very simple backup CBF. I know for other systems, you might wonder, okay, will it always be this nice? So let me kind of give you a few examples. This is an example I included in this paper where we have this lane keeping problem for Dubin's car. And then we're comparing an HJPD solution, which is basically our ground truth for the maximum control invariant set, right? It's like the biggest safe set you can find. And then we're using sum of squares as a kind of like a baseline for computational methods to compute such a set. And we're comparing these two with the backup CBF. So here, we simply take a moderate LQR gain as the backup policy. And you can see it's already, the backup CBF actually is, so the control invariant set corresponding to the backup policy is actually larger than the sum of square. It's still slightly slower than slightly smaller than the HJPD result. But then if you crank up the gain, you use a very aggressive LQR gain as the backup, you can see it almost pretty much recovered the HJPDF PD result. Here's another example where it's a classic aerial, like 2D pursuit example that you see, for example, in the in the Berkeley Hamilton-Jacobi toolbox, right? It's a classic example. So again, if we simply take this backup controller to be minus Umax times a sine of delta y, which is basically just trying to avoid the pursuer, then it's almost indistinguishable to look at these. Like the Hamilton-Jacobi result and the backup result is almost indistinguishable. So I'm not saying that this will happen for every example, but I'm just saying if you have some intuition of how to pick the backup policy, like it's actually quite nice. It will not be as big as good as the Hamilton-Jacobi, but then it's much easier to compute. Okay, so this is for the single system, a single agent problem. I know I have used a lot of time, but this is kind of necessary to talk about the actual multi-agent system. So yeah, now let's dive into the multi-agent problem. Why I talk about this backup policy, you'll soon see. So now let's say we have a multi-agent system where we have xi equals dot equals to some dynamics. Here we're assuming they all follow the same dynamics, but it can be different, right? Just usually when you have a swarm of robots, they're usually like homogeneous. But yeah, so if you do centralized control, then it's trivial, right? You just treat everything. You just treat it as a single agent system, essentially, right? Just you're finding the control U0 all the way to UN for all of the agent, then yeah, it's trivial. But usually what people are interested in is decentralized control. In other words, we don't have the computation power to compute, to have like a central controller for every agent. So we each agent have to come up with their own control input. So what should we do? So in this case, we have to make an assumption And the assumption is that the invariant set S and the state constraint C are defined pairwise, which is, I think, a fairly reasonable assumption, because usually for these systems, what we care about is just they don't collide with each other. So collision avoidance is actually pairwise. And the control invariant set, you'll later see that they can also be like nicely decoupled, and I'll show you how. And the second assumption is that each agent can observe the other agent's state, right? It's not a partially observed problem. It's fully observable. That might be strong. So, but let's just assume it's true. Okay, then we can talk about decentralized CBF. So the decentralized CBF QP, I actually skipped a lot of detail, but basically the idea is that we use exactly the backup policy CBF. Okay, and then now as you can see here, we have like HI for each agent, which is basically some constraint that only concerns a single agent. We also have HIJ, which are like safe constraint concerning two agents, for example, obstacle avoidance. Then if you write down the decentralized CBF QP, you'll see all these terms where some terms concerns UI. So this is the CBF QP for the ith agent. Obviously, I'm skipping a lot of detail, but conceptually, just follow me. This is the CBF QP that the ith agent would have to solve, and that CBF constraint concerns UI, which is the input for agent I. It also concerns UJ for all the other agents. Let's say I equals to 1, then J can equal to 2, 3, 4, all the way to N, because you're trying to avoid collision with all the other agents, right? So obviously, we're solving a decentralized control problem. We can only control UI, but we have all these terms that are unknown. So how do we tackle this problem? Well, it turns out that the solution is actually quite simple. We simply ignore them. Yeah, just assume they're zero, right? If we assume they're zero, then this problem is a solvable problem, because we only have the input for agent I, UI, and then we know from all the backup stuff that if we simply plug in pi I of xi, which is the backup policy of xi, then this term becomes zero, and when the CBF condition is positive, when the CBF function is positive, then this is satisfied. So we have a feasible solution, assuming all these terms are zero, right? And yeah, this is guaranteed to be zero, to be feasible. And we do this for every agent, okay? Just assume all the other agents' influence is non-existing. And then the magic happens. Why? Because we're doing this for all the agents. So by symmetry, even though these terms are not zero, but they're upper bounded by, for example, let's consider this condition. This term also appears in a symmetric way in the CBF QP for the J's agent. So the J's agent is solving the same thing, and we know that this term is upper bounded by negative alpha of Hij. So when we add those things together, as long as we're doing this for all the agents, we simply add a 2 here, okay? So we simply multiply by 2 this alpha function, and alpha is a class K function, so 2 times alpha is still a class K function. Then we have our CBF condition to be guaranteed to hold. So in other words, as long as every agent kind of work in harmony, so this is like a kind of like a visual illustration of what the idea is. So let's say we have all the agents, and this is all the feasible control for the ith agent and for the jth agent. Then this CBF QP actually removes part of the feasible part of the control where it doesn't satisfy the CBF QP, and this serves as a contract between agent. So if every agent is doing its own part by not like hurting the safety constraint too much, and the other agents are doing the same, then jointly they can guarantee safety. So it's a pretty interesting phenomenon. And then because of this kind of nice decomposition, this is purely decentralized. You don't need to know anything about the other agents. You only need to know their state, which is observable by assumption, and solve your own control and expect others to do the same. Then you can guarantee the safety for the whole system. So let's consider whether this is a feasible method for some of our typical multi-agent, multi-robot system. Here we have two examples: the Dubin's car, where the dynamics looks like this, and the constraint is basically the L2 distance between every two agent is above some threshold R. Then we can write down our S0, the small control invariant set, by adding the condition that vi equal to 0. So by the same kind of logic that we see in the double integrator case, right? The small control invariant set can always be defined just by finding an equilibrium point. So if you have an equilibrium point inside the safe set, then it's always a very convenient control invariant set to use, right? It's a single point, or it's sometimes it's like a manifold, like a lower dimensional manifold in a higher dimensional space, but it's still a control invariant set, right? Although it's very small and it's almost not usable, like it's almost not practical at all if you directly use that for safe control. But it turns out it's a very handy choice for the backup approach. And similar for the quad rotor model, it's a very complicated, like 17-dimensional model or something like that. I don't quite remember the dimension, but it's very high and nonlinear. But still, you can write down the safety constraint because they're pairwise decomposable. We simply care that every pair of the agent do not collide with each other, and you can write down the S0 similarly with all the velocity being 0. Then you have CBF QP that's guaranteed to be safety, to be feasible, and it can be solved completely decentrally. So here are some example. This is the first. Let me show. This is the Robotarium in Georgia Tech, and we haven't even seen the robot because they allow you to just upload your code and then they will run the experiment for you. So yeah, this is just 3 robots, and then there are 6 robots, and then purely decentralized, running the CBF QP online, and then they can, guarantee safety. Let me show you some interesting. Yeah, they're trying to go to different places and figure out, how to not hit each other. And we also have this 16-dimensional quad rotor example. This is in ROS. So if you don't have contract, they collide. Whereas if you have this backup CBF as their contract, even for such a large dimensional system, we can solve the CBF QP online, and basically ensure they don't collide.
Quick question on this one. So maybe I didn't quite follow, but how are you sure that they're not both going to try to avoid to the right and then avoid to the left and then vice versa and do this kind of chattering between each other? That makes sense. It seems like one commits to going to the right and one commits to going down.
Yeah, so in this particular example, we're using the same joystick to control their motion. It's just like reverse them so that it's like kind of mirroring the control. And then the way that one move to the left, one move to the right is completely the result of the CBF QP, because they're trying to minimize the distance between the actual input and the legacy control input, which is from the joystick. And then they naturally just find, okay, if we unless it's like perfectly head to head,
okay,
then it will stop. Yeah, but as long as there's some bias, it will resolve that. And then for the robot case, yes, we do see sometimes. So remember, the CBF QP only guarantees safety. It doesn't say anything about how well it performs. So we do see for some choices of the legacy controller, the CBF can get stuck. So
sure.
we have to do something so that it's smarter than it become it's using some smarter strategy, and then it will avoid getting stuck. But the point is CBF will guarantee safety for you, and you don't have to worry about safety. Yeah.
And then there's one question in the chat. It says backup policy is much easier than HMI. I'm not sure what HMI is. Maybe it's HJI. I'm not sure. In terms of problem formulation complexity or easier in terms of computation power. Yeah, HJI.
Um, I think, okay, if you talk about HJ, first of all, HJ still gives you theoretically the best thing. So that it's something that we cannot guarantee for the backup. Backup you can only like empirically try to find a nice at zero to begin with. You can try to find a nice backup to use, and in some cases it will kind of match HJ. So that's the difference in terms of for problem formulation. I think both are very, very flexible because both can deal with like just general nonlinear dynamics. Whereas like some of methods like sum of squares, they're more restrictive. In terms of deployment, it is more difficult because you're solving a CBF QP with the backup policy with all the flow map differentiation. So we have seen that it's still very, very lightweight. Like comparing to MPC, this is still quite easy to solve. But it is more computation demanding than just the vanilla CBF, let's say, which is
For the online, but for the offline, the compute for generating the HJI thing would take so much time compared to this.
Yeah. There's no offline step for this guy.
Yeah.
For backup, there's no offline. Yeah.
Right. And a couple other things that I really like about the backup policy while we're on this. One is that it allows you to bake in very easily like common sense intuition for a lot of these types of problems where do we really need to be solving in a dynamic programming way that when you're on the boundary of safety, you want to brake really hard. Often you can put in that user common sense intuition into it and get really good results with that. And then the other thing being this implicit representation, at least in the HJI case, we run into some issues sometimes of having these non-differentiable points. And so trying to guarantee that you have a smooth control invariant set is challenging. And so being able to instead use a backup controller for something like this can be, I think, powerful. Anyway.
Yeah, I think for the last point, when it becomes non-smooth and sometimes there's kinks, usually using backup CPF will make it smooth, but then you sacrifice some like safe region as a result. So yeah. Okay. And okay, moving on. So we have some extensions. So here we're talking about like if you start with, so the backup CPF will only be feasible will only guaranteed to be feasible when you're already in the safe set, but sometimes you're not, you start with a point where you're not inside the safe set. Then this is talking about like starting from a negative CBF value, we're using ADMM to kind of do not optimal recovery, still in a decentralized way. And then we have, like I said, the computation can be an issue when the dimension is high because you are solving this adjoint ODE. So we can directly learn a Koopman operator for the flow map, and then you can just differentiate that instead, because Koopman basically is saying for any mapping, you can sort of approximate it with the linear system in the higher like feature space. So this is a nice way. We have some videos of this Koopman back. Oh, I don't know why the video is not working. Anyway, so yeah, with the Koopman, we can make the computation for the CBF-QP super fast, and then we can train a neural network that's super scalable. So this is like 1,000 drones, and then this is also 1,000 cars, and we can guarantee they don't hit each other. So basically, we're just training a neural network that emulates the backup CBF. And then we can also deal with time delay and uncertainty, because basically the backup CBF turns the CBF function problem into a trajectory problem. You're basically reasoning about the trajectory under the backup policy, so you can reason about like how much effect does time delay has on your system, how much does uncertainty propagate through time, stuff like that. Okay, so summary, this is what Sylvia asked me to do, list the pros and cons for the first part of my talk. First of all, it guarantees safety. It's not like the neural network approach where you just kind of roughly guarantee safety. This is absolute. And it's applicable to most nonlinear systems. And I think particularly for multi-agent systems, this is very, very appealing. I haven't seen other methods that's so nice with respect to multi-agent systems. The cons is like, first of all, not complete. So you will not get the maximum control environment set in most cases. It's slightly heavier online computation than vanilla CBF, and it requires full control over all agents, which is really why I'm not working on backup CBF anymore in NVIDIA, because yeah, so that's a nice transition to the next part, the second part of my talk. Okay, yeah, so as I said, people don't cooperate, at least not like machines, right? Even in, I don't know, in the pandemic where we feel like, oh, I don't want to take a vaccine, I don't want to wear a mask, stuff like that. So yeah, we just cannot expect people to cooperate like machines. But on the other side, we are sort of cooperating, right? Or there's order within chaos. So this is a in the section in Africa without traffic lights. It's just crazy how, like all these cars are moving while not hitting each other. So that's something we are dealing with in autonomous driving. So I will first just say this. I think in the presence of human, guaranteeing safety in the traditional sense is just not possible. You can simply do this thought experiment where you're driving on the highway and then there's a car on the left, and let's say he's a psychopath and try to kill you, right? There's no way you can avoid that. He will hit you. Otherwise, like the police will not do like the US police has this famous, I think it's called the I don't remember the name, but it's basically like hitting the rear end of the vehicle and then make it kind of rotate 180 degrees. That's a way to stop criminals, right? So the reason why the police can do it is because there's no guaranteed safety. Otherwise, the police would have no way to hit any like escaping cars. So let's just put it, let's just take it as a fact, right? There's no way we can guarantee safety. So how are people typically reasoning about safety in the field of AV? Well, there's this ontological methods, for example. So basically, ontological means we try to rationalize human behavior, right? There are like game theory, POM-DP, inverse reinforcement learning. Basically, just view the human driver as an agent, which is trying to optimize some utility function, and then we can basically reason about it. So I will argue these methods are interpretable, which is nice, but not that scalable because usually these problem setting has to be handcrafted. You have to define, okay, there are an agent with, and then what's their goal, and when you have a new like unseen road geometry, all those things break. So it's not really scalable, and it's not that accurate, right? Human don't always try to maximize some utility function, at least not strictly, right? We're quite laid back and random decision makers. And then there are methods where it's like it's building on top of the ontological method, but it's trying to add some uncertainty to it, and then it's trying to quantify the uncertainty. So then there you have the conformal prediction, random convex program, scenario approach, and sometimes people trying to kind of verify neural networks. But yeah, so this is an example where it's like predicting the possible kind of motion primitives given the scene, and then use that for planning. So I would argue it only gives you stochastic safety. And stochastic safety is not that useful in practice, mainly because their number is still pretty high. Like we have to kind of guarantee, I don't know, one fatal crash in 10 to the 10th or 10 to 9th miles driven, and these methods would never give you some result like that, right? Just they don't deliver result like that. So then I think the mainstream of AV safety is the phenomenological method, which basically just give up on the hope of guarantee safety in any way. Let's just try to maximize the performance. Like if I can design a system where it doesn't hit, like it hit the least car in practice, then it's a win, right? If that safety level is good enough, then I can make money out of it, and then I don't have to kind of claim that I can guarantee safety, right? Because human doesn't guarantee safety. So as long as I'm doing decently well, then we're good. So yeah, unfortunately, that's what's happening right now. So today I will talk about like prediction plus planning. This is a typical scenario where AV has to deal with the uncertainty of the human decision makers, and then we have to make our own decisions such that we maximize our safety in the process. So typically, this is how a typical AV stack works. You have some perception that gives you bounding boxes. It reads the traffic signs, and then you use some machine learning methods to give you prediction, which is predicting like multimodal trajectories. So by multimodal, I mean, for example, this car, it can choose to turn left, it can move straight. You always have a multiple. It's not a unimodal like a Gaussian distribution. It's usually multiple modes. And then we try to plan accordingly. So prediction plus planning is this part. We assume that all the perceptions are done. We know where the vehicles are, where the obstacles are, and there are like super large quantity of works out there. In case you don't know, like machine learning is like just probably the hottest area right now. Every year, a lot of papers got published. And then the question is like, most of the methods they're focusing on prediction, and they're saying, okay, if we can guess correctly what the vehicle is actually doing, then it should lead to better. Then it should lead to better performance. But is that the case, right? What is the essential techniques we need to achieve like good closed loop performance? So let me give you a moving example. So for trajectory prediction, you usually generate multiple modes, and then the way you measure your accuracy is by saying, does one of the mode fit the ground truth, right? So if one of the mode correctly predicts something similar to the ground truth, then you consider this to be a success. But when we apply this multimodal prediction in planning, it becomes a very challenging thing. Why? Because let's consider this simple example where you're driving, the autonomous vehicle is the blue vehicle, and then there is a human vehicle in the red. And yeah, there are multiple choices. Like the red vehicle can maintain lane, you can change to the left lane, you can change to the right lane. You cannot just say, oh, okay, one of the options is not possible. Albeit very low probability, let's say 5%, is still a possibility. So when you have this multimodal prediction, what do? Do you consider the most likely mode, in which case you might be considered naive, right? Because what if it does the unlikely thing, then you will not be prepared. What if you consider all modes, in which case you're probably too conservative because like you cannot even move past this red vehicle if you are worried that it will change lane. Or do you do use some probability threshold? It's just this simple problem becomes tricky when you have multimodal prediction. And especially when the prediction horizon is long, the uncertainty just explodes. Right? And I know, Sylvia, you definitely have this experience where when you're computing the reachable set with the long horizon, it just becomes like unusable in many cases. So our intuition is that human decision making happens sequentially, right? We follow a tree naturally we follow a tree style thought where if you look at the same issue, the previous scenario, this is probably what's happening. So if you're only thinking about, okay, let me predict the future trajectory for the next 3 seconds, then maybe you have these 3 modes, right? 80%, 10%, 10%. But what's really happening inside the mind of this red vehicle driver is probably this. So he might think, okay, I have 80% chance I will maintain this lane, and 20% chance I will make a lane change. And as I'm making a lane change, I will actually observe what this blue vehicle is doing. So if the blue vehicle yields, meaning it slows down and allow me to do the lane change, I will proceed with the lane change. If the blue vehicle kind of accelerates and then he's claiming his space, then I'll just abort and then move back to my original lane. So if you only look at the trajectory for the whole horizon, you don't get this kind of sequential decision making in the process. So this is where we're missing. So by searching a single optimal trajectory for the ego vehicle or for the autonomous vehicle, we're ignoring all the future observation. I know this is kind of confusing because future observation, they are by definition happening in the future, and then we don't have access to that in the current time. But instead, what we can do is that we can kind of predict what might be the future observation and kind of enumerate them. And many people will argue, okay, because we're replanning, right? The ego vehicle, the autonomous vehicle is like updating its own plan every, say, 0.1 second at a certain frequency. But replanning is not a solution because every time you replan, you're still solving the same trajectory optimization problem. You're still finding a single trajectory, and all those issues I just mentioned will persist. So I want to argue that instead we should actually plan a tree structure motion policy. Instead of a single trajectory, now we're talking about a motion policy. So I'll actually skip this slide. This is talking about like what kind of suitable prediction model we want. But basically now we need a multi-stage prediction model that emulates this human thinking process, right? It's like rolling out this multimodal prediction in several stages such that it also is formulating a tree. Yeah, and then so this is our first work that tries to do this motion policy instead of a single trajectory. So here we have an analytical lane-based prediction model. So this model is only predicting whether the human vehicle will change lane, and it's a handcrafted model just to kind of do some concept prove the concept. Then yeah, this is multi-stage and it's ego conditioning because it basically we have this feature where the probability of a lane change will depend on the actual scenario. Okay. And then it's differentiable because it's a handcrafted, like heuristic-based prediction model. Then we can basically formulate this scenario tree where we have branching nodes and non-branching nodes. So at every branching node, we'll basically consider like multiple choices, whether this human-driven vehicle will change lane or maintain lane or slow down. We basically enumerate we enumerate a finite set of choices, and then we do this for multiple rounds at different depths. Then you generate a tree, and then once we have this scenario tree, we follow this old paper called min-max branch model predictive control, and we formulate a trajectory tree. So this shares the same topology as the scenario tree. We're basically saying for every branch of the scenario tree, we try to plan the trajectory for the ego vehicle accordingly. And we can linearize the dynamics, and then we basically linearize the cost, and then we can solve this this branching MPC problem by a single optimization that tries to kind of calculate the optimal response for all the scenarios. And then what's interesting here is that when we linearize the cost, we get these two terms. The first term is like if we fix the cost for a particular branch, how does our action change the branch probability? So it's like if I don't want the human vehicle to change lane, I might nudge forward so that the prediction model would assume that it will have less probability to change lane. Okay, and then the second term is basically okay, if we fix the branching probability, then we're just minimizing the cost for each branch. And then we'll I know I kind of realized that this is hard to explain, but then we have this tuning knob, which is a risk measure. I kind of probably won't go into detail here, but basically using this risk measure, we can smoothly transition between the worst case MPC versus the risk neutral MPC, which is just minimizing the expectation of the cost. But let me just show you an example of the highway overtaking that I just mentioned. So here, the red dotted line are the predicted trajectory, the possible trajectory for the human driving vehicle. I know the color coding is kind of flipped. I apologize for that, but this was a old work, so the animation was generated back then. But now let's just make it clear that the red vehicle is actually the autonomous vehicle, the blue vehicle is the human driving vehicle, and then here we're showing the result of the traditional planning where we're planning a single trajectory. And in this case, because there's a probability that the blue vehicle might change lane, it will just not be able to just move past the blue vehicle. But if you use the branch MPC, you get this nice behavior where it's like planning a tree structured policy, and it's able to realize that at a certain point, the probability of the blue vehicle changing lane is very low, and it's able to make the lane change. So here I'm showing the probability of different branches. You can see that the first stage is basically the ego vehicle, the AV is trying to nudge forward, making the probability of a human vehicle lane change very small. You can see that this is W3, which is the probability of the blue vehicle making a lane change, and it becomes very small, then the autonomous vehicle is able to make the lane change. Here's another example of merging. So in this case, the autonomous vehicle is merging into a highway, and then you can see here we're taking a snapshot where at this particular point, you can see we have like two branches for the different reactions, for the different options of the human vehicle. So if the human vehicle, which is the blue vehicle, maintains the fixed speed, then the autonomous vehicle will actually brake. So as you can see, the negative acceleration, and let the blue vehicle pass first. Whereas if we expect the human vehicle to decelerate, then it will actually accelerate and then cutting in front. So it's like constantly doing this kind of hedging between the two options, and eventually it will choose to yield. So this is another example of this French MPC. It's kind of, I don't know how well okay. So in this case, the small robot is controlled by the branch MPC, and it's trying to get to the start, which is the goal. And then the large quadruped is actually controlled by human operator, and it's just trying to be a nuisance and trying to block the small robot. And then you can see like the branching motion policy, which kind of is having different options for having different response for different possible actions of the large robot. Yeah. My PowerPoint is complaining.
Oh no.
Sorry, okay, finally. Yeah, and then we have some expand. I guess I can just quickly go through some of the remaining slides. Basically, previously the branch MPC kind of requires that the prediction model is differentiable so that we can put everything into an MPC, but that's not always the case because for many deep learned prediction models, the gradients are very expensive to evaluate. So here we have a kind of a sampling version of the similar approach where we're generating the trajectory tree and then a scenario tree. So the scenario tree is describing how the environment will behave, and then trajectory is kind of our option. And then we basically combine the two together, and then we get a finite horizon. Skipped it. We get a finite horizon Markov decision process where the state is just the trajectory tree node, and the scenario tree node. The action is what ego trajectory we will take next. And transition is basically determined by our prediction model. And then we can just, again, solve this Bellman equation. And I'll just show you the result. Here, we're showing some closed loop simulation of a autonomous driving scenario where this guy with this branching trajectory is the ego, is the autonomous vehicle, and then we're actually randomly kind of spawning agents just to make it more challenging. And the reason why you are seeing this this much more complicated scene is because previously when we have this branching MVC, everything is handcrafted, so we can only handle with this like simplistic kind of 2-agent case. But now this is using a state-of-the-art kind of deep learning model, so we can handle this complex thing. And I'll skip the quantitative result. Basically, when we are doing this like policy planning, it's much better than planning a single trajectory. And yeah, this is the conclusion. I have to skip a lot of detail because I know it's hard to explain all the details. But something to keep in mind is the takeaway message is that in autonomous driving, guaranteeing safety 100% is just not possible. So what we strive to do is just to get better empirical performance in terms of safety. And because of this kind of closed loop nature of the planning process, we realized that planning for a single trajectory is just not gonna be enough. So we turn to this policy planning idea which is planning a reactive policy that reacts to future observation of the environment. And then it raises like new requirements for our prediction model, for example, differentiability. And we're just trying to bridge the gap so that we can have the best policy planning algorithm with the least requirement for the prediction model. And this is actually something I've been doing with one of Sylvia's students, Sander. I don't know if he's here, but really, yeah, we're trying to continue working on this realm. And yeah, we have some ongoing work in NVIDIA, but really it's combining safety with just the sheer performance of the AV stack, because safety alone is not enough. If you just park your car in a garage, it's always safe, but it's not useful. So yeah, we're combining data-driven methods with like more traditional I guess control and planning methods like MPC, like barrier function, like Hammond-Jacobi, to build a safe AV stack. And then finally, I want to say, like, we are always welcoming interns as well as academic collaborators. So if you're interested, let me know. This is like an advertisement at the end.
All right, perfect. Thank you so much. That was wonderful, and I'm impressed with how much you were able to cover with still giving detail on all of it. We have one question in the chat, and maybe it's kind of related to your you need to give up on safety thing of asking if the tree motion planning can give you the optimal solution. And if you wanted it to be optimal, what conditions would that involve? And maybe a follow-on, could you talk a little bit about the relationship between this and POMDP work?
Yeah. So first of all, in terms of optimality, uh, there's no ground truth for optimality for this problem because you don't really know what the agent would actually do, right? If you assume that your prediction model is giving you the correct, it's giving you the correct distribution of the future behavior of that agent, then yes, we can guarantee safety, guarantee optimality because it's a POMDP. So, it's a finite horizon POMDP. So if you solve it, then you get the optimal solution. But that's only for the finite horizon. Beyond that horizon, naturally in the POMDP, usually you have something like a terminal cost, right? To cover for the infinite horizon, we just don't have that. If you train another neural network that predicts that as well, then we can bake that in. But right now, what we have is just a finite horizon MDP, and then yeah, with that we can guarantee optimality. But how valuable, how much weight does it carry? I'm not sure. Sorry, what's the next question?
I think that covered both of them.
Okay.
All right. Any other questions from the audience? Uh, okay. I guess I'm curious if you see your backup policy stuff ever making its way back in, or is it just because you have to rely on, for the multi-agent case, the symmetry? Do you feel like you're setting it aside for
Good
the
question. I also yeah, it's sad to let it go. It's not entirely irrelevant right now. So we actually there was one project where we use this backup policy flow map idea to construct something similar to HJ, which is like a measure of how, like, for example, if I'm driving on the current at a certain speed, I want to
Mhm.
know like what's the safety margin I have, right? And you can do that either with Hammond-Jacobi or you can do that with backup. So we're still using backup policy in that way, but we're not solving CBF QP online to ensure safety. That's just
Yeah, of course.
it's hard to do that. Yeah.
Regardless, even with that, I mean, you still need to do this sort of planning around agents type of thing in these types of environments for longer horizon. It makes a
Yes.
lot of sense.
Yes.
Okay, well, with that, we are at the end of time for class, so I guess I will let people go. But thank you again for spending so much time with us and going through all of this. I appreciate it.
Oh, thank you for the opportunity. It's a great experience.
Yeah, of course.
Yuxiao? Sorry,
Oh,
I had one quick question if
oh,
you can stay a minute.
Yeah, yeah, sure.
Um, so with regard to your backup policies, which was very, very cool to hear about. Um, so I imagine once you've actually like formed some sort of set that, your backup set, if it's not the whole like HJ reachability set, presumably you can use some like sum of squares method or something similar to find a new seed set in the complement of this like um, backup set. And I was wondering, like, I guess you didn't talk about that, and I imagine because there's something going on there. Like in practice, is it not that useful to have multiple seeds?
so first of all, the backup, the invariance that induced by the backup policy would always be larger than the original set you begin with, the S0. That's just by definition. So if
Right.
you have multiple seed, yeah, that would be great. And then it's actually very easy to write down the condition because now you're just doing a union of two sets. And in an implicit CBF QP, you simply add a max, right? Like you have two conditions and then you only need one of them to satisfy. Then you just add a max and then you can solve that CBF QP in the same way. In fact, we have a example where we have multiple backup policy. So it's not exactly the same as you describe. You're describing you have multiple seeds, But let's say you have multiple backup policy. With each of those backup policies will yield a different set, and you can actually solve that backup CBF online. It just within the multi-agents case, there's some kind of like synchronization thing you have to satisfy, and then we actually also write down the condition for that in the paper. So yeah, definitely this is very flexible. Like, just take max, take min, whatever, and it can incorporate multiple seeds, multiple backup policy.
Cool. Okay.
One thing that Sander has explored too, the student that we both work with, is taking the backup policy to help do the heavy lifting for Hamilton-Jacobi reachability. If you can get most of the way there, as you saw in the figures you were showing us, using the backup policy, then you can initialize with that rather than initializing from the terminal cost like we normally do, and then iterate on refining the rest of to recover the rest of the boundary of the set. And so it's also very useful for us in exploring how to get around a lot of the computational pain of dynamic programming.
Oh, sorry, that was it. Yeah, I appreciate that.
Professor, I have a question. Yeah. Yeah, I wanted to know, like, whatever the policies we are talking about at NVIDIA, it is still in the simulation mode, or like we have tried those policies in the real autonomous cars also sometime?
Yeah, so for autonomous driving, most of the research happens in the virtual world, which is, and that's not just for NVIDIA, like for almost every company running vehicles on the road. First of all, it's very risky. You have to you have to abide by a lot of the regulations, and you can do a lot in the virtual world. So yeah, I would say most of the research starts with the simulation, and then when it's mature enough, it will go on the car.
And it feels like more and more is able to be done in the virtual world now.
Yeah,
that's amazing. Okay, with that, I do want to let people go since we're past class time. So I'll let you all go. And Yuxiao, thank you again so much. I really appreciate it.
Oh, thank you. It's also my pleasure. Thank you.
Yeah, of course. I hope you feel better soon.
Yeah.
Okay. Bye, everybody.
All right, bye.